For nearly 50 years, buying a computer meant making one default choice. You bought an x86 chip from Intel or AMD. It was a monopoly so entrenched that most of us never even thought about what was inside our machines. The era of that single-path default is shifting. Recent performance benchmarks for Apple's M series and Qualcomm's Snapdragon chips have demonstrated that ARM can now run native desktop environments with the speed and stability of a traditional high-end workstation. If you are about to drop $1,000 or more on a new laptop or workstation, you suddenly have to make a choice about processor architecture. Pick the wrong one for your specific workflow, and you might find your battery dead before lunch. Or worse, your critical applications might simply refuse to open. This matrix shows two entirely different realities. On the left, the traditional x86 experience often means a 4-hour battery life and loud cooling fans. On the right, modern ARM devices push past 18 hours of battery life, running completely fanless. To truly navigate this split market, you need to understand the physical engineering differences etched into the silicon itself. Think of the CPU architecture as the foundational language a computer processor speaks. This language defines exactly what commands the chip understands, how it processes your data, and how it communicates with every other component on the motherboard. x86 and ARM function as two distinct dialects. They serve the same ultimate purpose, but they are built on engineering logic that approaches the same problem from opposite directions. Neither approach is incorrect. They were simply built from the ground up using entirely opposing engineering philosophies. Because these core languages are distinct, they physically dictate how much power a device draws and how efficiently it can execute your commands. The x86 dialect dates back to 1978, when Intel released a silicon chip called the 8086. This architecture was built to power the heavy, stationary machines of the early personal computer and enterprise era. It prioritized raw capability over energy efficiency because these computers were permanently plugged into a wall. As a result, x86 developed a unique superpower that is also its greatest constraint: strict backward compatibility. Software written 45 years ago can still technically run on a modern Intel chip today. ARM's lineage is entirely separate. It was created in 1985 by a British company called Acorn Computers, the team behind systems like the BBC Micro. Acorn's engineers had a distinct mandate to build a much simpler chip that ran at faster speeds, using a fraction of the power. The x86 architecture carries decades of accumulated engineering weight to maintain universal compatibility, while ARM was forced to start lean out of pure necessity. To see how this plays out physically, we have to look at their instruction sets. x86 operates on CISC, Complex Instruction Set Computing. This diagram illustrates how CISC functions. On the left side, x86 processes multi-step operations, like loading data, adding numbers, and storing the result, all bundled into a single complex instruction. The problem is that these instructions vary in size, from 1 to 7 bytes. To understand them, the chip requires large physical decoding hardware, which creates a bottleneck before any actual processing even begins. On the right side, we see ARM's approach, RISC, or Reduced Instruction Set Computing. Instead of variable sizes, ARM breaks complex commands down into 3 simpler, separate steps. Every single instruction is exactly 4 bytes long, allowing them to flow rapidly through a much smaller decoder. Shrinking the decoder releases billions of transistors on the die. This physical space is repurposed into an expanded compute pool, allowing the chip to process more instructions in parallel without increasing the size of the silicon. x86 dedicates immense silicon real estate just to figure out what it's being asked to do, while ARM squeezes more actual computing work out of its hardware. That transistor efficiency translates directly into power consumption. A typical x86 desktop chip draws anywhere from 65 to 250 watts under heavy load. Compare that to a mobile ARM processor, which sips only 1 to 15 watts of power. Dropping the wattage cascades into the rest of the physical design. Less power generates less heat, which completely eliminates the need for loud cooling fans and allows manufacturers to build incredibly thin, lightweight devices. At the scale of a server farm, a processor that uses less power yields massive savings in electricity and cooling costs, delivering up to a 40% improvement in price to performance. The rivalry is forcing both sides to adapt. Intel is now adding smaller efficiency cores to its processors, while ARM chips are scaling up to handle intense, multi-threaded performance workloads. Despite this convergence, the foundational DNA of each architecture still dictates which processor you should buy for specific tasks. To make the right choice, let's map your workflow on this chart. The vertical axis represents raw brute force and legacy support, while the horizontal axis tracks mobility and power efficiency. If you are a mobile professional who prioritizes an all-day battery, a fanless design, and modern productivity apps, you sit firmly on the right. You should choose ARM. If you are a high-end gamer or an editor who relies on legacy Windows plugins, discrete graphics drivers, and Steam's back catalog, you need maximum compatibility. You must stick with x86. And if you are deploying scalable cloud infrastructure where cooling and electricity are your primary operating costs, ARM provides the optimal balance. Evaluate your actual daily requirements rather than relying on brand loyalty or marketing hype. Your ultimate decision comes down to matching the native language of your critical software to the physical reality of the silicon.